Okay, so we're finally starting the last strand on trigonometry, which is how we look at construction and design. Trigonometry stands for the study of triangles. Okay, so trig stands for the triangles and ometry is study. And so just like geometry is the study of shapes. So, key thing to remember is the difference between congruent figures and similar figures. Congruent figures are identical shapes and are the same size, whereas similar figures are the same shapes, but they're different sizes. So the first thing that we're looking at is 7.1, 7.2, which is similar triangles. So we have to remember they're going to be different sizes, but they correspond to each other. So the triangles formed by a tree and a boy to shadows are similar. So if we have the sun shining past a tree and a boy, we could see that we have two right triangles formed. We have a big triangle ABC and we have a smaller triangle DBE. Okay, and the angles correspond. So we can look at, well, what does everything go to? So if we want to prove that triangle ACB, so going to the right angle, is similar, so that's the single wavy line, to triangle DEB, okay, so that makes sure that we have to label in the same direction. Okay, so we went from top vertex down to the right angle over to the third vertex. So when we want to label our angles, so ACB and DEB are both 90 degrees. ABC is the same as DBE because if we look at the bigger image, we can see they're the same angle. So therefore we can say that angle BAC and BDE are also going to have the same measurement because of our sum of interior angles. Okay, that all angles add up to 180 degrees inside a triangle. So therefore, triangle ACB is similar to triangle DEB because all three pairs of angles are equal. Okay, so that's a key thing. All three angles have to be equal to each other on the different triangles for them to be similar. So, example 2, name the similar triangles and explain why. Okay, so looking at this scenario where you have one triangle and a second triangle, what would be the similar triangles and how could we justify that? So I want you to pause the video, study the triangles, and then press play when you're ready. Okay, so if we look at these two triangles, if we pick our bottom left corner, D, okay, that triangle DEF of going along the two isosceles sides is similar to EGF because we can see that it's an isosceles triangle, so our two small angles have to be equal. And then also because our scale factor, this side is also 6. So 6 to 2 is a ratio of 3. So 18 to 6 is also a ratio of 3. So we can see the relationship between our side lengths is the same for both of these. So that means our angles will be the same. If we look at our second example, B, using these two triangles, if you want to think of the corresponding angles, you could rotate this triangle, okay, and put it next to it, and we would be able to see that ABC would be the same as EDC. Okay, so we cannot see that because ABC is the right angle, as is EDC. We can also see the X pattern, so we know that our angle BCA is the same as DCE. And then we can see our finer angles, okay, from the Z pattern. Okay, our Z pattern is formed from our right angles being parallel to each other. Okay, we can also see that the ratio of our side lengths are also equal of 8/3 of our big to small. Okay, or you could do what the ratio of your isosceles or sorry, of your right angle triangles are. All right, so next we're going to look at another example. So once we know that the two triangles are similar by proving that the angles are equal, we can solve for our unknowns or our scale factor, which is k. Okay, so our scale factor k can be found from the ratio of our corresponding sides from our similar triangles. And we're always going to use big to small. All right, so example 3, find the unknown side length. So you're given these two triangles. The first thing you have to look at is, are these similar triangles? All right, so from our indications, these are both right triangles. And then this symbol here of a single arc in these angles means that they are the same measurement. So since two angles are the same inside a triangle, the third also has to be the same. So yes, so these are similar triangles. So now we can look at our ratios. So remember, you're going to do big to small. So you pick your big triangle and you set up a ratio that you know. And then you set it equal to your other ratio and you're able to do your calculations. So try and do that yourself and then come back to the video. All right, so we can determine our scale factor, big to small. Okay, so 10 to 4, our k value is 2.5. So there's two different ways that we could calculate our x. We could either set up our ratio of big to small equals big to small, so 10 to 4 equals the corresponding sides of 6 to x, and then multiply both sides by the denominators to get rid of the fractions. So 10x equals 4 times 6, and then divide by 10, so 24 divided by 10. Or you can take your scale factor, k, and multiply it by small to get your big. So we have 2.5 times x equals 6, so divide by 2.5 and we end up getting 2.4 in both cases. So you could do it either way. All right, so how do scale factors for areas compare? Okay, so there's various ways that we could go about that. If we're looking at this scenario, okay, find the area of triangle ABC, we would need to know the base and the height. Well, we know the smaller similar triangle, we know its base and its height. So we can determine, well, what's our scale factor? So go ahead, determine what your scale factor is, determine what the height of the bigger triangle is, and then calculate your two areas. And then figure out, well, what is the ratio of your areas, big to small? So pause the video and then come back when you're ready. All right, so doing our scale factors, big to small, 15 to 8 gives us a scale factor of 1.875. Don't round it, leave all your decimals. So if we want to find what our question mark, our height of our bigger triangle is, we take our scale factor times our small triangle's length, and we get 16.875. So the area of the big triangle will be base times height divided by 2, which gives us a value of 126.5625. And the area of our small triangle will be base times height divided by 2, which will give us 36. So how does that compare to our scale factor? Well, when we find the ratios of our areas, we get 3.515625, which happens to be our scale factor squared. So the scale factor for area is k squared. So the area of a big triangle is equal to the scale factor squared times the area of a small. And that's because if you think about it, you have two dimensions, base times height, that have both been multiplied by the scale factor. So you've actually multiplied it by k and kept everything else the same. So that's why it works out to be k squared. So the final example is to find the area of a big shape that is similar to a small shape. So you don't know the shape sizes, so you don't have any formulas. All you know is that the small shape has an area of 52 and has a scale factor of 1.5. So what would be the area of the bigger shape? So think about it for a second, pause the video, and when you've come up with an answer, press play. All right, so hopefully you thought of the area of the small times the scale factor squared. So 1.5 squared would give you 2.25 times the area of the small, 52, gives you a big area of 117 square meters. So you're going to go ahead and practice some problems. I want you to do questions 4 and 5 on page 333, and questions 1, 5, and 7 to 8, only parts A and B, from page 347. We'll work on the more word problems application type in class, and I'll answer any questions that you guys still have.